question now, please. You are going to need your note sheet out from last Wednesday. So you're on with your periodic trends on it. So if you could grab that out right now, that'd be fantastic. Also, if you did not grab a worksheet as you came in the room, you're going to need one of those. It's periodic table 3. Or said you should have grabbed one as you came in today. Your note sheet from last week. Not the element poster, Rick. That one. You're in your right hand right now.
Note sheet.
Yeah. Note sheet from last week. Okay. So let's get those out. Let's get going here. We're going to be reviewing for our quiz tomorrow. So we have one little thing that we're going to be talking about that's not really new, but a little bit, I guess. And that's going to be on the quiz tomorrow as well. And then we're going to review everything else that you should need to know. I want to go. Here, I got it. You got it. I'd like to go over some of the upcoming assignments that we have. So, if you did not turn in the ventilative activity on Monday, which is probably like, I don't know, 5% of people, and literally almost everybody else turned it in. But if you did not turn it in on Monday, that is due today. So, you need to make sure that you staple the sheet that went with it, and then obviously your completed table along with it stapled on the back side. So, don't forget when you do that to have your conclusions. So please make sure that you have written out, you know, exactly how you figured out what each element was. Okay. We are having the periodicity quiz tomorrow in small groups, so obviously it's going to be able to be completed in a small group time. Periodic table 3 is going to be due tomorrow. That's the review for your quiz. So shouldn't be any surprise there. You might have a little bit of time to work on today. The big thing that's due tomorrow is the element poster. So you should be working on these, or you should have been working on these for a while now. A couple things to remember. You need to have your sources on the back. So, and you should have more than one source. So any place that you went to and that you use information from, you need to include that URL. So we're not asking you to go out full MLA format on us or anything, but you need to include the link to any resource that you use online. Also, if you're wondering what you need to do to get full points in there, literally look at the rubric and follow right along with the rubric. So if you put your name on the front instead of the back of it, you're going to lose a point. Like, it's just that simple. It says name on the back. Right? We don't just do that because. Okay, so please follow along to a T and you'll get all the points that you need to for that. A couple other reminders with that. Remember that you need to have your element name, symbol, atomic mass, and atomic number. They need to be broken up, right? If you can't have those all from one printed out thing. So you need to be a little bit creative with that in order to get full points. They need to be full size so that somebody can read them from a distance. Okay? You need to make sure that you don't have things that are hanging off your poster. And your poster, the last thing, it has to be oriented portrait, not landscape, okay? So they all need to be portrait when you're done. And that's just so that they fit nice and neat together when we create our periodic tables in our room. If you did not grab your colored paper yet, you need to grab that colored paper as well. So I have the colored paper for myself and Mr. Blackford. I know if you didn't get yours from Mr. Gussie, you're going to have to stop down there at some point today and get that correct colored paper because that's worth, I think, 2 points as well. So make sure you have the right colored paper. Okay, so grab it before you leave today. Stop down there at some point. Does anybody have any questions on anything relating to the element poster or anything that's going to be due in the next couple of days? Perfect. All right, so right now you can take out your worksheet that I just gave you, and we're going to add a little something else to your note sheet. Okay, on your quiz, you're going to be asked to be able to do this thing on whether or not something needs to gain or lose electrons to become stable. So if you're talking right now, I would stop talking because you're going to probably get this part wrong. Okay. You're going to be able to have to tell us if something needs to gain or lose electrons to become stable. So we need to know when an element is stable. And so we have something called the Octet Rule. And all the Octet Rule says is that elements, or atoms, we'll say atoms are stable with 8 valence electrons. Okay, valence is the same thing as outer. This is why the most stable elements are the noble gases, right? When we always say something is inert, it's because the noble gases have 8 valence electrons. The reason that other elements react is because having 8 electrons or 8 valence electrons is going to be the least energy that something can be. So when we talk about why things react, we're always going to talk about in terms of energy. Okay, so 8 electrons is the lowest energy that is going to exist. So things are going to either gain or lose electrons until they have that 8 valence outer electrons. So we're going to talk about whether it's more or less energy to gain or lose, and that's going to be different and depend on how many valence electrons different elements have. Okay, so we're going to take a look at sodium and chlorine just to start out here. Okay, and so the best way to do this is to look at the orbital diagrams and then be able to determine, how many electrons it needs to become stable. So we're going to start with sodium here. So we're going to write out just the orbital diagram for each energy level. So in sodium's first energy level, it has a 1s sublevel, just like every other element, and it has 2 electrons in that 1s sublevel. Okay, well, this is be familiar from the things that we did last unit. Okay. We still need to get to 9 more electrons for sodium. So we know, especially if we use the periodic table to write electron configurations, that sodium is also going to have 2 electrons in a 2s and 6 electrons in a 2p. So we can write out 2s here and fill it in with 2 electrons, and then a 2p and fill that in with 6 electrons. Now, that's not all of sodium's electrons yet. It needs 1 more, right? It has 11 electrons. So we're going to need to write a 3s sublevel, and there is 1 electron in this sublevel. Now, I wrote the electrons on here in different colors on purpose. What are the blue electrons called right now? The ones that I drew up here. Those are called our inner electrons, right? So when we talk about chemical reactions and stuff, the inner electrons, so that's literally all these guys, are not really interacting at all with other elements, okay? So the only electrons that are going to be interacting are these valence electrons, or the outer electrons. And sodium has just 1 of them, correct? So if I asked you to write out the outer configuration for this, so that's something you're going to also have to do. It says the outer electron configuration. When we talk about outer electrons, it's literally the furthest out ones. So all we would write here for sodium is 3s1. So sodium's outer electron configuration would be 3s1, because we don't care about the 2p's or the 3s's or the 1s's. Why? Because they're not contributing to the reactivity of the element. Okay? So the last thing that we need to decide here is, in order for sodium to become stable, so to be at a low energy state, what is it going to need to do with this 1 electron? Is it going to give that electron away to get 8 electrons, or is it going to be gaining 7 electrons to gain 8? Okay, that's what we need to decide here. So if we take a look here, if I take away sodium's 1 electron, it's left with a complete second energy level that has 8 valence electrons, which we just got done saying is stable. So do you think that's going to be easier or harder than it finding or gaining 7 electrons? What's going to take less energy? Huh? Losing it, exactly. So down here we're going to circle lose, and it's 1 electron. Because it is going to do the thing with the least amount of energy possible. So it will not gain 7. Now we're going to do the same thing for chlorine. So we're working on a couple of things that we need to know for tomorrow. So we're going to draw its first energy level. The first energy level is the 1s, and it's the same as sodium's. Everything in the same row is going to have all the same inner electrons. Does that make sense? So sodium, magnesium, and aluminum, silicon, phosphorus, sulfur, chlorine, argon, those are all going to have the same exact amount of inner electrons. So our orbital diagrams should be the same. So the second one here, in my 2s, I'm going to have 1, 2 electrons, and then my 2p is going to have 6. The difference in electrons here is going to come when I get to this outer configuration. So once again, when I talk about outer configuration, I'm only talking about the furthest out electrons, the valence ones. So for chlorine, it has 7 valence electrons. Does anybody remember, or do we remember how we know very easily that chlorine has 7 valence electrons? If we look at the periodic table. Yes, no? It is group 17. Or group 7A. The 7 in that 17 is literally telling you how many valence electrons it has. So chlorine has 7. Fluorine has 7. Bromine has 7. What about the noble gases? How many do they have? Is group 18 or group 8A? What is that 8 telling you? 8 valence electrons. Okay, so the oxygen group would have 6 valence electrons. Look at the 6 up there. Not 16, but 6. Okay, look at the nitrogen group. It has 5. Carbon group 4. Boron group 3. Okay, the alkaline earth metals have 2, and the alkaline metals have 1. Okay, we are not talking about the transition metals right now when we talk about those. So we're only talking about those main block elements. We need to remember how to do that. Okay, so we know chlorine right now is going to have 7 valence electrons. So I'm going to put those in these outer levels here. So in the 3s, we're going to have 2, and the 3p, we got to have 5 more for a total of 7 in this third energy level. So now, for chlorine, is it going to be easier for chlorine, so is it going to be less energy for chlorine to literally lose all 7 of these electrons and drop down to look like this right here? Or is it going to be easier for chlorine to just take 1? To gain 1 electron. What's the least amount of energy that's going to be taking place here? Gaining 1, exactly. So we'd circle gain 1 electron. So hopefully this makes sense to us. This is why things like sodium chloride exist, because sodium would be potentially giving that electron away to chlorine just like that. You don't need to draw the arrow on here. I'm just showing you this. So now, I don't want to know the outer configuration with this electron, but I want to know what's the outer configuration for chlorine right now. All I'm worried about is that S sublevel and the P sublevel. So I would write out 3s2. So for chlorine, it's 3s2, and it's 3p5. And if we're paying attention right now, the outer electron configuration is literally noble gas notation without the noble gas. Does that make sense? So we should be fine with this from last unit. Okay, so we just aren't adding the noble gas in there. So if I ask you what the outer electron configuration was for silicon, you would say 3s2, 3p2. Okay, so we should be able to do that pretty easily like that using the periodic table. Okay? Questions on that right now? All right, I'm going to talk just briefly about ionization energy. We're going to go through a problem on ionization energy. What ionization energy is saying is it's the amount of energy required to pull an electron away. Okay, so what this chart's telling us is it's telling us that electron 1 takes this much energy, electron 2 takes this much energy, electron 3 takes that much energy. So if we're looking at this, sodium is the very, very first one here, okay? And this is helping us conceptualize what's happening over here. Sodium, it says, takes the least amount of energy to lose its first electron. Why would that make sense? Because sodium's only 1 electron away from being stable. So it takes a very low amount of energy to take this electron away. Okay, so the next electron, electron 2, now that sodium is stable, is going to take a significantly more amount of energy to take away. Okay, we need to know this because in a minute we're going to do one where we deal with trying to determine the number of valence electrons here. So it should be obvious to us that sodium has 1 valence electron according to this electron energy, because look at the difference in energy required here to take the next electron away. Okay, if we look at something like magnesium, the next one, well, magnesium has 2 valence electrons, so even though it takes a little bit more energy away, comparatively it's not a lot. If we look at how much it takes to take magnesium's 3rd electron away, it's a considerable amount more energy, and that should make sense to us, and that's because it's an inner or core electron. So those ones are going to be held very tightly. It's going to be very hard for something to pull those away from these elements. Okay, so we're going to talk about magnesium and phosphorus now too. We're just going to walk through these relatively quickly because I think we're getting the gist of it right now. If we're looking at magnesium and phosphorus, they're going to have the same configuration for energy level 1 and 2 as sodium and chlorine do, right? So we'll stick with our same colors. The first energy level, so the 1s, is going to have 2 electrons. Okay, our second energy level for both of these is going to have a 2s with 2 electrons, a 2p with 6. The difference here is this final energy level. So how many valence electrons does magnesium have? If you don't know, look at the periodic table. We just talked about these, so you're going to need to be able to do this for tomorrow. So how many does it have? How many? 2. Right, it has 2. So that means we got to put 2 electrons here, right? Now, what's the outer electron configuration for magnesium? Just 3s2. Perfect. So you'd write, well, let's write Mg here so we know what we're talking about, and we write 3s2. Okay, phosphorus, same thing here. Okay, it has a 1s with 2 in it. It has a 2s with 2 electrons, and it has a 2p with 6 electrons. Now, phosphorus has how many valence electrons? Somebody burn out how many does it have? Huh? 5. It has 5 valence electrons. Very good. So we have to fill those in. So we're always going to fill the s first with 2, and then the 3p will have 1, 2, 3, because we need to have 5 in this 3rd energy level. Okay. Then when we write out the outer electron configuration, it's going to be 3s2 and 3p3. Lastly, now for phosphorus. Phosphorus is either going to have to lose 5, it's easy to see here, right? If it loses these 5, now it'll have 8 valence electrons, or it's going to have to gain 3 electrons. So obviously, which one's going to be less energy? Gaining 3, exactly. So you'd circle gain, and you'd put 3 electrons here. And I'm sorry, we said magnesium, but I didn't write it, but it's going to lose 2. Okay, so that's what you'd do for these. Take a look at silicon quick, please, and then you can do the rest. Silicon's at 4, right? So is that going to gain or lose?
It could go either way.
Can go either way, exactly. Can go either way, and then it just has to be 4. Right, so circle both, circle whatever, circle 1, but it's 4. Okay, now, do we have questions on anything I just did right there? Okay, yeah, it's a good question. What about argon? What do we think argon is going to do? Huh? Exactly, Lucas. What did you say? Nothing happens. So for argon, nothing is going to happen. Argon is already stable. We said the noble gases are stable with 8. So for argon, it's going to stay exactly like it is, because it already has a full 8 outer electrons. We're good? Perfect. We're going to do one where we look at successive ionization energies. Okay? There's 2 parts to this type of problem. Okay, we're only going to do one of these right now. You have 2 on your review sheet. If you're still confused after that, please come and see one of your chemistry teachers. Okay? Now, we have to be able to determine, first of all, how many valence electrons each group has. Now, I just went through this, right? We said group 1 has 1 valence electron, group 2 has 2, Group 3A or 13 has 3. Group 4A or 14 has 4. Group 5A or 15 has 5. Oxygen group has 6. Halogens have 7, and noble gases have 8. We just have to be able to look at it and just know that right away, because that's we got to be able to do that in order to answer this type of problem. Okay, so what you're looking at right now is the amount of energy required to literally take an electron away. So if we flip back to these pages, it's that E1 that you're seeing is how much energy it would take to literally grab this electron away from sodium. Does that make sense? It would be like showing how much energy it takes to take this first one would be 738 for magnesium, and the second one would be 1451. So it's showing us how much energy it's taking to remove electrons. Just to give you a little context here, it's not just a number that means nothing. So what we're looking at is literally the energy required to take one away. So if we're looking at this, for this element that we're dealing with here, to remove the first electron would take 578 joules of energy, or whatever it is, okay? It's less than that, but that's not important right now. Okay, what we're looking for is the big jumps in energy that are occurring. So what we're trying to find is where is the largest jump in amount of energy required to remove an electron. So if we look at this, the energy required to remove this first electron is relatively low, right? Does that make sense if we look at the rest? Now you might look and see, okay, it jumps by 1,300. Now that seems like a lot, right? If you just call it good there and say it has one valence electron, you're going to be wrong, because what you're looking for is where it has a relatively large jump. So we need to be able to compare numbers here. So we look at the next one. Okay, that's not that big. We look at this one. Okay, now it's only 900 difference. Now look at the jump from 3 to 4. It's taking 2,700 here all the way up to 11,000. So that would be like our red flag. That's where a large change in energy is taking place. Does that make sense, everyone? Okay, so we would have 1 electron lost, 2 electrons lost, 3 electrons lost. Now that is stable, right? Now after this third one here, this is where the element is stable. How do I know that? Because this one takes a large amount of energy to take away. So wherever that large amount of energy taken away is because that atom is holding that electron tight right now, right? It's not able to let go of it very easily. So that one is where we're going to have a core electron. So what I'm trying to say is, when you're trying to determine the number of valence electrons here, it's always the number before the jump. Does that make sense? So don't call this 4, because when people will get these wrong, what they'll do is say it has 4 valence electrons because they put it right here. Okay, it says 3 valence electrons. Wherever the large energy is where it's now a core electron. It takes a lot of energy to take that away. Okay, so now we would write that it has 3 valence electrons. So we can't determine exactly what element this is because there's more than one element that has 3 valence electrons. So we can say what group this is from. So which group is this from? And I just need numbers here. 13, or when you do this, you just have to write group 3A. Okay, it's when we do main block, but they'll give that to you. So it's 13 or 3A. Those are one and the same. Okay. Is everybody good with that type of problem? Okay. Does anybody have questions on how we do that? Okay, awesome. All right. Very last thing that we're going to need to do is periodic trends. Okay. And I'm going to show you that you need to memorize these for tomorrow. Okay, you have to know them. You're like, wow, I have to memorize 4 different things. All you really need to know is 1. Okay, and I'll show you what I mean. Okay, so when I get these tomorrow, I would write these out on the test. So I get my test, I write it out just so I know which way it's increasing. But if I know the atomic radius trend, I know all the others because all of the others are exactly opposite of atomic radius. So electron affinity, ionization energy, and electronegativity, they all trend exactly the same and in the same direction. So if I'm going in, know that atomic radius is increasing down to the left and it decreases up and to the right, well, then I know that the other ones are exactly the opposite of that. So when I get my test tomorrow, if I'm you guys and I want to do well, I'm writing this out here right away, and I'm writing one of these on there right away just so I know. Okay, that's the first thing I would do. So then you can just use it as a guide because all the other ones are exactly the same. So they're all going to increase up and to the right, and they're going to decrease down to the left. So should have took whoever was a terrible singer.
Whatever. That wouldn't be nice. We don't want to do that.
Okay, so like I said, if we know that atomic radius increases down to the left, we know all the others increase up and to the right, so that can help us when we're going through. The only other thing that we need to worry about is when we have positive or negatively charged ions. So this is something that you just have to remember and know for tomorrow. Okay, so we should always be knowing that negative ions are going to be bigger, and that's because they have more electrons. They're not able to hold those electrons as tightly. Okay, positive ions are always going to be smaller because they're able to hold the electrons tighter, closer. Okay, so what we're asking now, which of the following have a smaller atomic radius? If I write this on here, it's really easy for me to know. If I'm dealing with charges, I don't even need to consult the periodic table. So I'm looking at chlorine minus or O2 minus. Now they have charges. All I'm looking for is which one is literally less negative in this case. Okay, so if oxygen is 2 minus, that one's automatically going to be bigger because it has more electrons on the outside. Okay, so we would circle Cl minus here. The second one, nitrogen or fluorine. Well, now we don't have charges, so we're going to have to consult the periodic table. We look, we know that things are getting bigger as we move from right to left and as we move from top to bottom. So is nitrogen or fluorine going to be smaller? Fluorine is smaller. It gets smaller as we move right. Remember, because it gets more protons, it's going to suck everything in closer. So we would circle fluorine in this case. Okay, number 3. Do we need to look at the periodic table at all for this one? No, why not? There's a plus there, right? As soon as I see that positive, what do I think? Is that one going to be smaller? Absolutely it is, right? Positive charge, we're thinking smaller. So we're going to circle that guy. Okay, last one, once again, it's a negative versus a positive. Negatives are always going to be bigger. Positives are only going to be smaller. So that one should be the easiest for us. And we would circle sodium. You don't, if you have, the only time, what's the only time that I need to look at the periodic table for atomic radius? When I have charges. When what? When they're equal. Yeah, when they're equal. So if I gave you 2 negatives or 2 pluses or 2 that were 2 plus, you need to look at the periodic table then. Okay, but otherwise, you don't need to consult the periodic table at all. Good? Awesome. Next one. Now we're working with the other trends. It says, which of the following have a greater ionization energy? So, like I said, all we need to know is the one trend. Well, everything else trends up and to the right is getting bigger, right? So we're increasing ionization energy as we move literally this way on the periodic table. So for the first one, we're looking at zinc or germanium. Zinc is 30, germanium is 32 for those of you that are looking at the periodic table right now. So all we're trying to decide is which one is up more and to the right. Okay, if they're in the same row like they are, it's going to be the one that's farther to the right. Okay, so we would circle germanium here. Okay. Now, the next one, we're looking at calcium or magnesium as being greater. Well, now they're in the same column. All right, so all we're looking for now is whichever one is higher. Okay, so is calcium or magnesium higher? Well, magnesium's higher, so magnesium has a greater ionization energy. Lastly, zinc or lead. Okay, now we're dealing with ones that they're not in the same row and they're not in the same column. Okay, so lead is much lower, zinc is higher, but it's a little bit further to the left. Don't overthink this. Which one is closer to that right-hand corner? Which one's closer, 30 or 82? Zinc or lead? Closer to the right-hand corner? So closer to fluorine. Zinc is closer. Like if we're talking about relative distance, zinc is closer to fluorine, so we're going to circle zinc. Okay? Questions? Good. One last one. We're going to do electron affinities. Electron affinity is letting us know which one is going to be more likely to grab electrons. Okay, so this one, once again, fluorine is the most likely to do that, so it's up and to the right again.
So I want to know which one has less though. So that's why it's going to help me to write the trend out like this. I think, honestly, I would write these trends out. Because the way people get confused the most, everybody, is all of a sudden this one says less, the next one says more, and we're like, just don't even overthink it. Just write the trend out on your test when you get it. That's what I would do. Just trying to remember that up until that point. Okay. So it's decreasing down and to the left. So I want to know which one has less. Potassium or magnesium. Well, potassium is further down and it's further left. So we would circle potassium. The next one, copper or silver. Silver is directly underneath copper, so we would circle silver. Okay. Gallium or manganese. Now they're in the same row. This is 31 and 25 for those of you that are following along right now. So manganese is further left. It's closer to that bottom left-hand corner, so we would circle manganese. And then phosphorus or chlorine. What do we think? Which one? Okay. Yeah, phosphorus. Exactly. Are we good on these? Okay, perfect. I'm telling you right now, the best way to help you be successful tomorrow is to write at least these two trends out on your sheet, okay, when you get it. All right, perfect. Take out, and we're going to play a Kahoot with labeling the different regions and families in the periodic table in a second. But before we do that, I want you to take out your review sheet. I need to go over the back of that for you quickly. Okay. Well, let's start in the front. I lied. Let's start in the front because this was a good question that somebody asked. Number 1 says complete the following table, and then it says the name of a trend in the middle. It says trend vertically and trend horizontally. All that is asking you is to name your trends and then describe which way they're either increasing or decreasing. It doesn't matter, whichever you remember better. So the first trend that we deal with is atomic radius. So I wrote that, how does the atomic radius trend vertically? So from top to bottom. And all I wrote was that it increases down. And what that means is like the size of the atomic radius is increasing as we move down the periodic table. And why? It's because we get more energy levels. Okay? Then this trend horizontally is that it increases to the left. So as we move from right to left on the periodic table, so from neon to lithium, from argon to sodium, from krypton to potassium, whatever, we're getting bigger. Okay? So it gets smaller from left to right. Remember, that's because we're getting more protons and it's sucking the atom in tighter and tighter. Okay? So you need to write the other trends in there, say how they trend. Okay, now we can flip it over. The back of the sheet is like a little puzzle for you again. Okay, starting out, these letters here, they're telling you the letters that are in a family. So basically, we have a series of clues, and it's 1 through 21. What I'm trying to do is match up the letters for clues on here with actual elements on the periodic table. Does that make sense? So, for example, U right now would be carbon. Okay, so I'm trying to match them up with something on there, so that's how I can use the clues to help me. Now, as soon as I know that carbon is U, I know the other members of its family must be G and N. Okay, that's how to use this. So that's why I wrote gun on the bottom here. So I know that either silicon is G or N, and germanium is either G or N. So I'm going to have to use the rest of the clues to help me out with that. Okay, so that's just how you go about that. Does anybody have questions on that? Perfect. You're going to have to use some of your knowledge of elements and things to go about completing that. It's just like a little puzzle. Right now, if you have a device, take your device out. We're going to play a little Kahoot. The Kahoot is all on labeling, because one of the things that you're going to need to do tomorrow is label the periodic table. You should leave your periodic table 3 out right now, because this Kahoot's not going to take the rest of the time. You're probably going to have between, I don't know, 10-ish minutes to work when we get done with this. So please utilize that time. I would try to do this without my notes right now, because it's not going to help you to know where you're at if you use your notes, honestly. So.
Also, everybody, you know that Kahoot has colors on the answers, right? Make sure you're aware of that before you do this, because I'm going to ask you like which block is shaded yellow or something, and so don't just like click the yellow answer right away if you get my drift on that. Well, I can't control which like color, right? That's what I'm telling you right now, so you don't mess it up.
Better stop right now, right? CK, you better stop right now. Did you do that? Was that Connor? Connor being dumb again?
Yeah.
You did?
I'm like, okay. I don't like that. And my favorite character is Cat.
See, it's fine if you do, but Connor did.
Alright, is that ready in? Are we ready to go? Is anybody not in?
He's just really oblivious to everything, so that makes me
Sorry.
Okay.
How does this make sense?
It's asking which one's shaded red. So I said don't look at the colors on the bottom of your green.
Okay.
That was my first piece of advice.
Okay. That confused me so much. I'm just like, oh, what?
Oops. That's what I said. Don't do it.
Okay, which one? This one I look dark blue on you guys. Sorry, but it's most reactive non-metals. That should be helping us out here. It's the one between the purple and the blue. Okay, everybody got this one. If you're struggling right now, you should use it.
ionizes the bottom down there. Obviously, we know that now. There you go. Doesn't say anything this time. Can I sometime? Inert means it does not react.
Every time I throw
Good job.
So I got that one. I got the one. Which one's
No color on this one, obviously. We should probably know this one.
Yeah.
Come on, guys.
Yellow. Choose yellow.
It's back. I got answer sheet to 11.
Someone's probably the person yellow.
Oh, no, it's teacher. Somebody always said.
Where's orange?
Oh, yeah, it looks a lot like red.
It doesn't look like that. It's the resolution changes in here. What I mean is it looks like
Press the color.
five clears to reach answer streak 8.
That's weird, because I'm on answer streak of 12 right now.
Well, it doesn't tell you everything on there every time. You want the credit, Liam?
Yeah, right up on the board.
Liam is on an answer streak. Let's go.
Yep. No, not anymore. No, I am.
Answer streak 13.
Make that 13. Got all of them right.
What's your name?
Lucas. What?
You're ever after?
Oh, I'm in 5th. I'm in 5th. Gusto. Good. Well, I finished this 5th.
There you go.
I got an answer sheet 13 too. What the heck?
So did Liam, everyone. We just wanted that to be clear. 13 too. I got your back. Alright, that's everything for today, you guys. You have about 10 minutes to finish up on periodic table 3. Well, not finish up, but continue to work on periodic table 3. Remember that's due tomorrow. Your element poster is due tomorrow. If you don't have your colored paper yet, you can come up front and grab that right now before you leave class today.
Mr. Oops. Do I go through our shirt? Yeah. And can I turn this thing in?
Oh, look at that. We got medals. That's fun stuff. Oh, it's good. Yeah?
Where do I turn this in?
You can turn it to the and then if you guys want to go for the trade meeting, Mr. Gussie, if you want to hit the... Thank you.